Chapter 6, Section 6 is bond angles and hybridization. When you draw a Lewis structure, and remember, Lewis structures are only for covalent compounds. When we draw Lewis structures, we can identify the bond angle and what's known as the hybridization of the molecule. So let's define what these are. First of all, bond angles, they result from the repulsion between the atoms in a chemical bond, and it's based on the number of domains that are around the center. So if there are two domains, which means you have a linear molecule, which would look something like this, the bond angle that's formed around the center atom is 180 degrees. If there are three domains, then you have a trigonal planar shape, and the bond angle around the center atom is going to be 120 degrees. And if we have four domains, then you have a tetrahedral shape, and these are a little more difficult to draw three-dimensionally. The wedge means it's kind of coming out front, and the dash means it's kind of behind. And in between, around the center of this molecule, you have a bond angle of 109.5. And this angle is the same between each. So just like this one's the same, 120 and 120 between those. There are bond angles for 5 domains and 6 domains. However, in this course, you don't need to know them. Hybridization is a very complex idea. The mixing of 2 or more orbitals of similar energies on the same atom to produce new orbitals of equal energies. That's the technical definition of a hybridization. However, basically what's happening is the atom is trying to maximize its bonding opportunity. Realize, looking at our diagram, that only single electrons are able to bond because they can share space with one other electron from some other element. And so right now, as carbon's structure stands, it can only make 2 bonds. However, if it were to take this electron and move it to here, then it's going to change its bonding ability. Because at that point, we're going to have 2s with just the first electron, and then you're going to have in your 2p orbitals 1 electron in each, and now you can see that carbon is able to make 4 bonds after moving that electron down to its empty orbital. It's the act of doing this is known as hybridization. So here's again carbon's diagram where originally the electron was here and it got moved over to here instead, no longer in the 2s orbital. And so we get what's called an sp123 hybridization. This is called sp3 hybridization. And it's because you have an electron in the s, and then you have 3 p orbitals with 1 electron. Boron has what's known as an sp2 hybridization, where the original electron was in the s orbital and then was transferred or moved over to the second p orbital. And in doing that, we have 1 in the s, and then we have 1 in the first p and 1 in the second p, and none in the third one. So this is known as an sp2 hybridization. Beryllium is an example of an sp hybridization, where again the electron in the 2s orbital moved over to the p orbital, and so here we have 1 in the s and 1 in the first p orbital, which we call an sp hybridization. So hybridizations for each of the domains is, if you have 2 domains, you'll have an sp hybridization. If there are 3 domains, we'll have an sp2 hybridization. 4 domains is sp3. 5 domains, we actually start hybridizing with the d orbitals. So you have sp3d, and 6 domains will have an sp3d2 hybridization. So to kind of summarize, if we know how many domains there are, then it's easy to identify what's the hybridization and what are the bond angles. And so if we look at 2 domains, recall that if you have 2 domains, the electron domain geometry is linear. The hybridization will always be sp, and the bond angles will be 180 degrees. 3 domains, you have an electron domain geometry of trigonal planar. Hybridization sp2, bond angle 120. 4 domains has an electron domain geometry of tetrahedral, hybridization sp3, and a bond angle of 109.5. 5 domains has an electron domain geometry of trigonal bipyramidal, hybridization sp3d, and again, we're not going to worry about the bond angles even though they do technically exist. 6 domains has an electron domain geometry called octahedral. The hybridization will always be sp3d2, and we won't worry about the bond angle. So let's kind of practice some of the following. We're going to identify the electron domain geometry, which we have labeled EDG. We're going to determine the molecular geometry, which is labeled MG. We're going to identify the bond angle, if applicable, which is labeled BA, and the hybridization, which is labeled H. So to do the first two, you're going to have to go back and use your notes that are in your notebook, and you're going to need to use the back of your periodic table, that chart. So let's look at CH3F. And in this case, we'll count the domains first. It has 1, 2, 3, 4 domains. So if we have 4 domains, it has an electron domain geometry of tetrahedral. Remember, because there are no lone pairs on the center, that means that both of these are going to be the same, tetrahedral, because this is actually a formula of AX4. Okay, the bond angle, because you have 4 domains, is 109.5, and the hybridization of 4 domains is sp3. The second one is going to be CNS. It has 2 domains. So if it has 2 domains, then the electron domain geometry is linear. The molecular geometry is also linear because there are no lone pairs. We have AX2. The bond angle is going to be 180 degrees, and the hybridization will be SP. CLF4 with a -1 charge has a couple of lone pairs on it. There's a pair and there's a pair. So this has a total of 6 domains, which makes the electron domain geometry octahedral. The A's, X's, and E's, we've got, I'm going to draw it to the right. We have an A in the center. You have 4 fluorines, so those are each X's. And then we have these 2 pairs, which are my E's. So this is AX4E2. AX4E2. And if we look at our chart, AX4E2 is square planar. The bond angle is going to be not applicable because I didn't tell you a bond angle for 5 and 6 domains, but the hybridization is going to be sp3d2, which is the maximum of the 6, of course. Okay, the next one is SO2. Notice again, we do have a lone pair on the top. This has 1, 2, 3 domains. So 3 domains is going to be known as trigonal planar. The molecular geometry, we have A with 2 X's and we have 1 lone pair at the top. So AX2E is what this one is, and that's going to be known as bent. The bond angle is going to be 120 degrees, and my hybridization is going to be sp2. BF3 has 3 domains, which makes both the electron domain geometry and the molecular geometry trigonal planar. We have a bond angle of 120 degrees and a hybridization of sp2. Last one is going to be SF6. We have 6 domains. Because there are no lone pairs, both of these are going to be considered octahedral. There is no bond angle that we need to list, and the hybridization is going to be sp3d2.